Now we are discussing the Gay-Lussac's law. According to this law, pressure of a gas is directly proportional to the temperature while keeping the mole and volume constant. If we remove the proportionality, we can write it as P equal to K into T, where K is the Gay-Lussac's constant. If we compare Gay-Lussac's constant with the ideal gas equation, we can find out that it is nR by V. In this problem, the pressure exerted by an ideal gas at temperature T degree centigrade means T plus 273 Kelvin in a vessel is 1 atm. When the temperature is increased by 10 degree means if we write it as T plus 283 Kelvin, then pressure increases by 10%. That is, if the initial pressure is 1 atm, now it is 1 plus 1 of 10% means 1.1 atm. Now the final pressure is 1.1 atm. We need to find out the temperature T, that is T degrees centigrade. Now the concept is P by T is constant as the volume and number of moles remain constant. So we can write it as P1 by T1 equal to P2 by T2. By placing the values, that is pressure P1 is 1 atm, T1 is T plus 273 and P2 is 1.1 and T2 is T plus 283. By solving, we will get value of T. So the value is minus 173 degrees centigrade. Now we are discussing the alternate method for the same problem. As the volume and number of moles is constant, so it means P by T is constant. Now let the initial temperature to be T1 Kelvin. So we know that pressure is directly proportional to temperature. If there is 10% increase in the pressure, it means that temperature should also increases by the 10%. The increase in temperature by 10 degree means that increase in temperature by 10 Kelvin, as change in degree centigrade is the change in Kelvin. So 10% rise in temperature is equal to the 10 Kelvin. So T1 equal to 100 Kelvin. And T1 is T plus 273, which is equal to 100. So T comes out to be minus 173 degrees centigrade. It's a very simple approach. Now we are discussing the Dalton's law of partial pressure. If in a container we take more than one non-reacting gases, suppose A, B and C, which we are showing with the different colors, then total pressure in this container is sum of the partial pressure of each gas, that is PA plus PB plus PC. There is another important result which we can derive from the ideal gas equation, that is we take PV equal to nRT. Here we are taking PT. PT means the pressure of all gases and V is the volume of container and NT is the total number of moles present in this container, that is Na plus Nb plus Nc. R is the gas constant, T is the temperature. We can also write the pressure for the gas A. If we want to write the pressure because of the gas A, that is PA, V, volume of the container will remain same for all the gases, so it is V, and it can be written as Na because we are taking the pressure because of gas A. So it is Na. We will consider only moles of A. RT. R is again universal constant, T is the temperature in Kelvin. Similarly, we can write the partial pressure of B in this container while taking PB into V equal to NB RT, and partial pressure of C, PC into V equal to NC RT. If we divide second equation by first equation, that is we can write PA by PT, which is equal to NA by NT. It means partial pressure of A is equal to total pressure into the mole fraction of A. Similarly, we can write for the partial pressure of B equal to total pressure into chi B. Partial pressure of C is equal to total pressure into chi C, where chi A plus chi B plus chi C equal to 1. This is the another important result of the Dalton's law. If we are taking more than one non-reacting gases in a container, then partial pressure of gas A is equal to the total pressure of the mixture multiplied by the mole fraction of A in the mixture. This we can apply in the air also. Air is a mixture of gases. We can find out the partial pressure of oxygen gas. We know that the total pressure of air is 1 atm, and we know that the mole fraction of oxygen in the atmosphere is 21%, that is 0.21. We can write partial pressure of O2 is equal to 1 atm into 0.21. That is partial pressure of oxygen in the air is 0.21 atm, which we can find out by using this Dalton's law. Now we are discussing the application on the Dalton's law. The problem is equal weight of ethane and hydrogen are mixed in an empty container at 25 degrees C. We need to find out the fraction of the total pressure exerted by the hydrogen gas. The weight of hydrogen and ethane in the container are equal at the same temperature, that is 25 degrees C means 298 Kelvin. Now we know that the partial pressure of H2 is total pressure into its mole fraction. So we can write it down as partial pressure of H2 upon total pressure equal to mole of H2 by mole of H2 plus mole of ethane. So mass of the hydrogen and ethane are same. So we can write mole in terms of given mass by molar mass. We know that the molar mass of hydrogen is 2 gram. So we can write W by 2 for hydrogen. Similarly, we can write for hydrogen here again W by 2, and in case of ethane again we are taking mass to be W because mass of hydrogen and ethane in the container is same. So we can taking it as W divided by the molar mass of ethane, which is 30, carbon atomic mass is 12 and H is 1. So we can find out that molar mass of ethane is 30. By simplifying, we can get that partial pressure of H2 upon total pressure means fraction of the total pressure exerted by the hydrogen equal to the 14 by 16.